जो होता है, ये is something which has been worked out for a column which is pin-ended. Now, a pin-ended column, if you look at it, has a curve which shows you that तुम्हारा effective length. See what is effective length actually? The effective length is the length in between the 2 points of contraflexion. And वो in the sense कि जहाँ पे भी तुम्हारा zero slope आता है, ठीक है, वहाँ से to the next place जहाँ तुम्हारा zero slope है. So if you look at a column and you look at the vertical line as your slope, so from the point where you're getting your zero slope to the point where you're getting the next zero slope, I mean, you will get two lengths. One you might get a lower length and one you might get a higher length. So the higher of those two lengths is what is considered as a. Can you see my mouse, guys? If I'm moving my mouse, can you see my cursor?
Yes, sir.
Okay. So if you look at this column, okay, either it is the full length, in which case यहाँ से यहाँ तक है, or it is from the point of zero slope, which is this point, to the next point of zero slope. तो अगर हम ये कॉलम देखें और fictitious एक दूसरा ऐसे कॉलम इसके beyond देखें, in the sense we extend this line and take another line here. So you will get one point here which will be zero slope, one point here which will be zero slope, and the distance between this will be L. So that is why you get a theoretical slope of, if place, again you are getting the same thing, that this is your point of zero slope, this is your point of zero slope, and the distance between this point of zero slope and this point of zero slope is L. So again you're getting theoretical value of K as
So there's a delay in the pointer. The pointer delay, it's delayed. So
okay. So, okay, then let me be very slow. Okay, if you see this point, okay, after that, if you next see this point, okay, the distance between this point and
so the
this
pointer
point,
isn't moving.
Oh, it's not moving. Fantastic. How do I do this now? यार मेरे पास पेन नहीं है यार, वो number at
So just tell me about the figure number, like you are talking about figure C or figure D.
Okay, so let's first talk about figure D. Okay.
Yes, sir.
Now, in figure D, I want to find out what is the distance between 2 points of zero slope. Okay. Now, the first point of zero slope is at half length of the column.
Yes, sir.
Okay. Now, if I look at this column as two columns, and ये जो slope ऊपर वाला slope है, उसके नीचे वाला column पे उसका slope में उसका shape में reverse कर दूं, तो उसका 0 point जो है वो उसके L/2 पे आएगा.
Yes, sir.
So the distance between the 2 points of zero slope will be L.
So we are like doubling the size of the column to check the points of zero slopes.
Absolutely. The doubling you are doing is just to kind of give you some kind of a sense of why this is L.
Yes.
Okay. Now, on the other hand, if I look at figure C, okay, at the absolute bottom, you've got zero slope.
Yes, sir.
And at the absolute top, you've got zero slope.
Yes, sir.
Okay. So the distance between these 2 points ends up as becoming L.
Yes.
Okay. Now I take a look at figure B. At the absolute bottom, you have got zero slope.
Yes, sir.
And at somewhere approximately 3/4 of the line up is again where you have got zero slope.
Yes, sir.
So the theoretical length here is 0.7. Okay.
Yes.
If I look at A, you can see now why in A your theoretical length is L/2.
Yes, sir. At half the length we have zero slope, and at the bottom we have zero slope, or at the top you could say.
Absolutely. So you get a effective length of L/2. If I take a look at figure E, okay,
Yes, sir.
Okay. Now, if I take a look at figure E, okay, if I जो मेरा ये फिगर है उसको ही मैं मिरर नीचे कर लूं, okay,
Okay.
then I will get a column of length 2L
Yes, sir.
and it will be like figure.
Yes, sir.
बराबर है? Now, figure D, we have figured out why it will be L. So, figure E will show you that why it will be 2L.
Yes, sir. इनको similar है,
Similarly,
similar है.
absolutely. But it is similar with twice.
Yes, sir.
So,
Similarly, figure F. Yeah.
So could you please explain
Yeah,
why
yeah.
it was L for figure D? Because when you were telling this, there was a lag in cursor. So will you please
Okay.
repeat it?
Uh,
Thank you.
so if you look at figure D, okay, if you look at figure D, okay, and you invert figure D below itself, okay, so you draw another abstract of figure D below that. और figure D का L है because actually तुम figure D का L जो है ना, that is your Euler buckling load. Okay, your Euler buckling load has already showed that for a pin-ended column it is L. So actually figure D को अब दूसरा explanation देखने की जरूरत नहीं है because figure D is what is your Euler buckling load defined for. Because your Euler buckling load is anyway defined for a pin-ended column with a length L. But
Yes.
if you want to graphically take a look at it and you want to fit this into the same slope concept that we are looking at, if you take figure D and you draw another same figure D below that, in the sense just assume that there is another column below that, and assume that figure D is a column which is swaying to the right, and assume that the column below that is the same column but it is swaying to the left.
Yes, sir, got you.
So what will be the distance between zero slope? It will be L because
Yes, sir.
L by 2 is from top to here और नीचे L by 2 for the दूसरे वाला.
Fine.
ठीक है?
Yes.
अभी फिगर E को तुम पूरा उल्टा कर लो तो it will start looking like figure D but with a length of 2L.
Yes, sir. Yes, sir.
So the theoretical value for figure E is 2L. Now if you take a look at figure F और figure F को उल्टा कर लो पर इस बार नीचे मत करो ऊपर कर लो. You will again get a pin-ended column with a length of 2L. And since we have already established that the theoretical value for a pin-ended column is the actual length, you can see that for figure E and figure F, why the actual length actually and the effective length actually ends up as becoming 2L. I can do this mathematically by actually just invoking your buckling equation. I hate to do things mathematically when I can actually do them visually, because I always feel that, at least for me, visual sense has always been something which has stayed with me. The mathematical sense has always been something which I've had to remember. But if I can visually take a look at it, it is something which it stays with me a lot better. So I try as far as possible to see if there are some visual explanations because they tend to remain with me a lot more. And I'm hoping that possibly you guys think the same way. But इसका एक mathematical explanation भी होता है. But उसके mathematical equation के लिए तुम्हारी in solid mechanics when you did columns and you found out what was the Euler buckling load, okay, you did that entire system which was based upon a bending moment and finding out what was the bending moment and adding ky as the as py as the additional bending moment on the system and finding out what was the eigenvalue of the equation. Now, when you do that, you can just modify your boundary conditions and you'll keep in this L, 2L, 3L, 4L. You'll actually end up getting Euler buckling loads, which will be pi squared E by L squared 4 pi squared E by L squared, 9 pi squared E by L squared, they will be squared multiples of L2L and things like that. Okay. So, or you can get a Buckling usually pi squared E by 4L squared if it is 2L kind of a thing. Sorry.
Sir, in the end condition code, there are four types of four types given. First one is fixed, second one is hinge, fourth one is free end. What is the third one? The rotation fixed and translation free.
अच्छा ये तुम कोड की बात कर रहे हो ना?
Yes, sir.
हाँ, कोड खोल के देख लूं तो मैं कोड शेयर करता हूँ तुम्हारे साथ, so then we can talk about it on the code. ये हाइड शेयर ऑप्शन शेयर करते हैं एंड कहाँ गया अभी मेरा कोड, कहाँ गया? हाँ यार कहीं पे तो मेरे पास कोड ये दिख रहा है, कोड दिख रहा है?
No, sir.
एक मिनट है, बताता हूँ। लेक्चर, हाँ ये देखो, ये कोड दिख गया?
Yes, sir.
Is my screen visible? Okay,
Yes,
so now
sir.
let's go and take a look. Let's go and take a look at the boundary conditions. So effective, हाँ ये वाले आ गए ना? These are the ones ना that you're looking at. Are these the ones you're looking at?
Sir.
हाँ तो ये काफी स्ट्रेट फॉरवर्ड है ना. टेबल 11 अगर आप कोड का देखोगे और इफेक्टिव लेंथ देखोगे, so this is where this is restrained and this is free. ठीक है? This is where this is a pin joint and this is a sliding roller, where your translation is possible, but the joint is fixed. So what does this mean? Where will you see this? So when you see a building where you end up getting, suppose you got a stiff slab, okay? If you've got a building with columns and you've got a stiff slab, a stiff floor, that the floor cannot rotate. So what you'll be ending up getting will be a sway in a building. Okay, so when you end up getting a sway in a building, this is the kind of image which will be generated. Is this making sense? Figure that's figure 2. Figure 3 is a pin-ended column, and figure 4 is a restraint at the bottom and kind of a sway at the top. Figure 2 is a sway at the top and a pin jointed at the bottom. And figure 4 is a sway at the top and a restraint at the bottom.
Is the name sphere?
I'm sorry, sway at the top. It's not
Okay,
one
sir.
word.
Okay, sir.
It is sway.
Okay, sir.
So I mean, I don't know. Okay, let me try and draw something here and hope that it comes out. I don't know whether this will work, but can you guys see me? Is my camera on? Can you guys see me?
Yes, sir.
अच्छा, ये दिख रहा है?
Yes, sir.
आपको याद है कि ऐसे प्रॉब्लम्स अपने स्ट्रक्चरल एनालिसिस में किए हुए थे?
The frame sway.
फ्रेम स्वे ये किया होता याद है?
Yes, sir.
हाँ, तो ये जो कंडीशन है ना, this condition is this condition B. This actually is condition B. Okay. अब वो condition B में at the bottom, instead of having it as a fixed joint, if you have it as a pinned joint, you will get condition B.
Okay, sir.
Is this making sense to you?
Yes, sir, it does.
So, of course, ये जो conditions हैं, ये 1.2L जो कहते हैं, these are not the, so there is a difference between what is, so now let me share the PPT again. Okay. Can you see the PPT now?
Yes, sir.
If you see this, there are two things. One is what is the theoretical value and what is the recommended value. So all the values which are there are all the recommended values. Here you're saying that there is a theoretical value also and a recommended value also. So if you see the theoretical value for condition C in this diagram, but the recommended value is 1.2. And why do we take a recommended value as different from the theoretical value? You always end up taking a recommended value as different from the theoretical value whenever you're looking at a fixed condition. Because whenever you're looking at a fixed condition, you're assuming in reality that there is nothing like a perfectly fixed condition. So the theoretical value 0.5, for example, in figure A, is assuming that your conditions are absolutely perfectly fixed, which does not exist in reality. There is always some form of a rotation of the support which happens in reality. So in reality, this theoretical value should not be taken, and what you should be taking is a value which allows a certain amount of rotation. So that's why the recommended values are empirical in some sense. And what you can see is that only a change in between the theoretical and the recommended value when you're looking at a fixed condition. There is no change between the theoretical and a recommended value if you're looking at a pinned connection. The change only happens when there is a fixed connection in place. However, you also see that in conditions E and F, although there is a fixed condition in place, there is still no change in the theoretical and the recommended value. And that is because 2L से ज़्यादा कोई भी चीज हो नहीं सकती. So, if your theoretical value has given you a value of 2, which is the upper bound of what can exist, then recommended value does not say that you take greater than 2. But as long as your theoretical value is giving you a lower value than what actually can exist as a pin-pin connect, then what it does, what your system says is that in which case you need to take a slightly higher value of k than what is the theoretical value. Is this making sense, guys?
Yes, sir.
I mean, I think I'm spending a lot of time on this slide, but I think that's good because I think understanding this is very important, because what is the effective length is always a judgment that you do. And I think understanding this is a very, very integral part of stream design. So is this slide clear, guys, everybody?
Yes.
Now, of course, you can also have something which are internal restraints, that you can restrain a column at its center point in some kind of a way. And these internal restraints are very important because what they do is they break down the effective length. Like, for example, the first case, your effective length was L, and in the second one, your effective length is now going to be L by 2. And how will we figure that it is L by 2? Again, let's take a look at what is the distance between the points of zero slope. And here you will see that the difference between point of zero slopes, if you've got a perfectly restrained curve, is going to be L by 2. Now, typically what you will end up saying is that it will not exactly be L by 2, because again, you're assuming that your lateral straight is perfectly in place. So you will actually end up getting maybe L by 2 and multiply that by 1.2, so you'll get maybe 0.7. But it is reducing your length from L to 0.67. So if you have got a long compression bar, uh, see, the thing is that as your length increases, you start getting buckling at lower and lower force values. Okay, so you might start with a column which is not going to be buckling until you're getting yield, until you end up getting up to yield. And as you increase the length, you'll start getting buckling at lower and lower forces. Okay, so the design of a compression member is always in some way also trying to see how do you restrict the effective length. Now, one way to restrict the effective length is to add supports. So if you have got a lot of supports, then you will by default restrict the effective length. Another way of reducing the restrictive length is like generating some kind of an intermediate restraint, which is not really a support, but it's some kind of a holding system together kind of a thing, and like bracings. Okay, and we'll take a look at a few bracing systems to see how the effective length is actually starting to get. But in this figure, you can see that adding a bracing is reducing your effective length. I mean, how much it reduces, let's not get into that. But it is definitely reducing it from L. Are we good with this?
Yes.
Whether it becomes L by 2 or whatever it becomes, L से तो कम ही रहेगा. यहाँ तक इतना तो हम accept कर लेंगे ना.
Yes, sir.
है ना? So now these are the different ways that you give bracings. So beams can be a bracing, but beams will be a bracing only in the plane in which they are bracing. You get my point? So now if I take a look at figure A, okay, I've got two axes of buckling. I've got one axis of buckling which is going to be in the plane of the diagram, and I'll have another axis of buckling.
So the slide didn't change.
Oh, it didn't change, is it? Ah.
So it's
Has it
still
changed?
showing effective length.
Ah.
So it's still showing effective length.
Okay, fantastic. Let me share it again. Now,
Yes, sir.
now you can see the intermediate lengths and effective lengths in different planes.
Yes, sir.
Okay. So now there are two planes of buckling. One is a plane of buckling which is going to be in the plane of the. So if I look at my columns and beams, my columns and beams are in one plane. Okay. So there's going to be one buckling which is going to be in, and I'm going to be having another buckling in a plane which is going to be perpendicular. Is this okay?
Yes, sir.
Now the adding of beams will only restrain the buckling in the plane of which the beams are being.
Yes, sir.
In the other plane, adding these beams will have no effect. The column will still buckle as a complete column in the other direction.
Yes, sir.
Okay. So this is actually the concept that when you add beams, and now we take a look at the the cross section of the column, and we had figured out that there was a stronger axis and a weaker axis. Okay.
Yes,
There was
sir.
one axis where you had a higher moment of inertia, and another axis in which you had a lower moment of inertia. Okay. Now, when we said that the buckling load is squared E divided by L by R squared, R is different in different planes. That in the minor axis buckling, R will root of I minimum by A, and in the major axis buckling, R will be the square root of I maximum by A.
Yes, sir.
Okay. Now it is always the minor axis buckling which is going to be more critical than the major axis buckling. And obviously now because buckling to your weaker axis में ज़्यादा easily होगा. So your bracing is always something which you are usually putting in the weaker axis. So if you have got a column, you would orient the column in such a way that it is the weaker axis gets braced and the stronger axis which doesn't get braced. If you have a choice of bracing one of the two axes. I mean, if you can brace both axes, try to brace both axes. But if you have a choice that only one of them can be braced, you would try to brace the minor axis rather than the major axis.
Yes.
Making sense?
Yes, sir.
So these are the different forms of lateral bracing. So this is also, so if I now take a look at the first figure on the, if I take the full length of the member, I can see that the member length can be broken by giving bracing into 3 members. Okay, so now each member will behave differently. So instead of having a column of size 3L, I might end up getting a column, 3 columns of size L. A truss does the same thing, that instead of having one long compression member at the tip, it breaks it by giving some kinds of diagonal members. So all members in a truss end up also reducing the effective length of the, so if I'm making a truss, which is let's say 30-meter long, I never have a single 30-meter long member. I might break up into smaller members using diagonals and things like that. So my member might end up becoming 4 meters or 3 meters or something like that. But the truss itself is 30 meters. So one of the reasons of the trusses is to break the length of the compression member. And by breaking the length of the compression member, saying that its buckling propensity gets reduced tremendously. Is this making sense, guys?
Yes, sir.
Then effective lengths of columns in simple structures. So in the z-axis, I might so if I've got this member here, I'll have a different L if I'm looking at the y-axis and if I'm looking at the z-axis. So in the y-axis, I'm seeing that it is a kind of a fixed kind of a member. In the z-axis, I'm looking at it as a cantilever. So I might end up getting a higher L if I'm looking at Z and a lower L if I'm looking at Y. Because again, when I'm talking about restraints are also planar restraints. So what is the length of the member also changes. And see, this is something which is a little difficult to understand physically, but you can understand it that the effective length of the member in the x-axis, in the y-axis, is dependent upon the restraints in the y. The effective length of the member in the z-axis is dependent upon the restraints of the member in the xz plane. So if the restraints xz plane are different than the restraints in the xy, you will have different ly and a different lz.
Yes, sir.
Okay, so I think that is what is important here also, that your effective is not just for a member, it is also for which direction of buckling are you looking. And you might have different effective lengths upon different directions of buckling. So let's take a look at figures A, B, C, and D. If I look at A, okay, I'm talking about a column without intermediate lateral restraint. Okay, so what I'm getting is that the length of the column is L. I have got a roof on the top, so the roof on the top ensures that my y-axis, okay, is kind of taken care of. Okay, now if my y-axis is taken care of, in the sense because it's restrained at that, what I end up getting is that my Ly is 0.85 L. On the other hand, my Lz, which is that in the Z direction, this member behaves like a cantilever member. Because the entire roof does not restrain this member from going in the Z direction. The roof is just restraining the members from moving in the Y direction. Is this making sense, guys? If I look at the roof, so if I look at the roof as a stiff beam, okay, so if I look at the Y direction, the stiff beam ensures that it behaves like a frame with a side.
Yes, sir.
Whereas in the Z direction, it will behave like a cantilever.
Yes, sir.
So when you look at effective lengths of columns in simple structure, in the Z direction, you have a different Lz than in the Ly. Now, on the other hand, if you have columns with intermediate restraints, intermediate lateral restraints to both flanges, okay, now in the Ly direction, it will be 0.85 L and L1, which is or 1.0 L2, whichever is lower. And again, this makes sense. And in the Z direction, it is still 1.5 L. In the sense that this is where I'm restraining the column in the y-axis. In my y-axis, there is a restraint. In my z-axis, there isn't. So, unless I start restraining my columns also in the plane, which is particular to the so if I look at this as a plane frame structure, okay. So if I've got lots of structures of this thing, I'll have several plane frames one behind the other. Unless I restrict all these plane frames with respect to each other, in which will be generating Z directional restraints. In the Z direction, all these plane frames will be as cantilevers. So, which is why even in a plane frame structure, it is important to restrain the structure in the perpendicular direction to the plane frame also. This is making sense, guys? The restraining of the structure should be done in both the directions to ensure that your effective length is curtailed in both your directions.
Yes, sir.
Okay. Also, this example is something which is just there to show that one should not rely on software completely, because very often software does not incorporate certain aspects of solid mechanics, which can be very crucial to that particular structure. So something like a torsional buckling is something usually is not incorporated in a software because it's a very it's a very painful thing to do. Now, there are certain sections which have a high propensity for torsional buckling. When you use those sections in a software, the software does tell you that the structure is going to fail. But in reality, that structure fails because solid mechanics and physics is actually more important than what software is. So this section, this is just to show you that when you do a software, when you do a plane frame analysis in a software, it doesn't tell you anything about the Z buckling, because the software just says that there is no force in the Z direction. You know, however, the Z buckling can be very critical for a frame if it is not restrained in the Z direction. Now, this restraint is not something that the software asks you to do if you do a plane frame analysis. Because in a plane frame analysis, the software is not going to tell you anything about what is happening outside the frame. So when you do a software-based analysis of it, to understand that the software has a set of limitations and that you need to have solid engineering judgment to ensure that that limitation doesn't actually translate into some form of a failure. Is this making sense, guys? Then let's go to the next one. So again, another thing which the software doesn't do well is tapered beams. Tapered beams are typically extremely difficult for something for the software to look at. And that the tapered beam ends up generating a torsion. Is a torsional propensity collapse is something which the software finds it extremely difficult to do because it's not incorporated in the sense it's maybe the problem of people who write because softwares are typically written for generic structures, but when you use some random sections which are not generic in a software, the software cannot deal with it. So I mean, all of this is to say that don't rely too much upon software. That's all. Flexural, torsional buckling, I'll take a different class of this. I don't want to confuse right now what is happening. But the flexural torsional buckling is the interdependence between flexure and torsion. That they are not completely independent structures, but that flexural behavior. See, what is buckling? Buckling is that your actual behavior is governed by your bending of the limb. You get my point in that whenever you did your actual Euler buckling solid mechanics, might have, I don't know how you did it, maybe you did it mathematically or maybe you did it through some way, but fundamentally the concept is that there is a moment which is generated because of the actual force. Okay, now if you look at the statics of a structure, an actual force does not generate movement. But when the beam bends, okay, and there is a certain displacement in the direction because of bending, the actual force generates a moment which is into this y, which is this bending, and this moment adds to your original moment, and that is actually what causes buckling when it reaches critical place where the interaction between your actual force and bending starts ending up generating higher and higher bending values. So that's why it's called an eigenvalue analysis, that it is a singularity of structure. This value of force that a singularity exists and that you end up getting because of this singularity uncontrolled and a cascading bending effect. So bending is a interaction between your axial and flexion. Similarly, there is an interaction between your torsion and flexion. So the interaction between flexure and torsion is what is called flexural torsional buckling, and the interaction between flexure and axial is what is called as buckling. I mean, because that's what is buckling. But to differentiate buckling from torsional buckling, flexural torsional buckling is the interaction between flexure and torsion. I will maybe talk a little bit about it, and maybe if you're interested, I will point you in a certain direction where you can actually figure out how this actually works. But as of let's understand that as we have an axial flexural interaction, it's also possible to have a flexural torsional interaction, because all buckling is fundamentally about an interaction of different responses. That a regular buckling is about the interaction between an axial and a flexural response, and a torsional buckling is the interaction between a flexural and a torsional response. So the concept is in all buckling problems, it is the interaction of one force with the other response. So in regular buckling, it is the interaction of the P, which is the actual force, with Y, which is the lateral displacement caused due to buckling. And similarly, in flexural torsion buckling, it will be T, which is the torsion, with the Y, which is the flexural displacement, which is caused because of flexion. So the interaction between the response of action and the action of and another action itself is what is a buckling system. So buckling is the interaction between the regular buckling interaction between the actual force and the lateral displacement caused because of action. So it is the interaction between one action and the response of another action. Is this making sense? Or have I lost you?
Yes, sir.
Making sense. fantastic. Very often when
A
I
little.
speak, when I make this, very often when I make this statement, very often I feel that I'm not making sense to myself. So अगर बाकी लोग कहते हैं कि it is making sense तो मैं काफी समझ जाता
It's
हूँ.
it was too much to take in. You spoke too much.
See, my point is that when you look at buckling, what is it that you're solving a moment equation?
Yes, sir.
Okay. Now, in that moment equation, you are adding in a term which is because of the axial force.
Yes, sir.
And what is that axial force term which gets added? It's into y. What is y? Y is the response due to flow.
Yes, sir.
And P is the axial force. So, this is happening. It is one action, and see, force is an action. What is an action? Okay. Y is the response due to moment.
Yes, sir.
And P is the action. So the interaction between one action and the response due to another action is what the entire concept of buckling is about in some sense. You get my point? It is an interaction between two systems. It is an interaction between an axial force system and a flex system. Okay?
Yes. Yes,
But
sir.
it is not an interaction between force and moment. It is an interaction between force and the displacement due to moment.
Okay, sir.
You get my point? Now the
Yes.
interaction between one action and the response of another action is what is buckling. And what does buckling do? That it generates a singularity. And what is a singularity? That you have a elastic stiffness, which is caused because of your flexure. You have a geometric stiffness, which is caused because of your traction. And that's why it's called geometry. Okay. Now, when this geometric stiffness and this axial stiffness become the same in magnitude, what happens is that the overall stiffness of the structure goes down to zero in that particular direction. And because the stiffness of the structure goes down to zero in that particular direction, you end up getting an uncontrolled response due to even a small force because the stiffness is zero. You get my point?
Yes, sir.
Okay. Now, if you look at your stiffness matrix, which is 12 VI by L cubed, that is stiffness matrix. Now, that is actually actual stiffness matrix, isn't it? Because it's a stiffness matrix which is because of flexion. Okay.
Yes, sir.
You get a geometric stiffness matrix which is because of axial forces. Okay, and that is why compression causes buckling and tension does not. Because in tension, the geometric stiffness matrix adds to the compressive stiffness matrix. In compression, the geometric stiffness matrix subtracts from the flexural stiffness matrix. Is this making sense? Because the direction of the force will change, na? What is the magnitude of the members? It will change the sign of the members, na? कि अगर मैं Py कहूँ, अगर P नेगेटिव होगा, तो Py भी नेगेटिव होगा, है ना? अगर P पॉजिटिव होगा, तो Py भी पॉजिटिव होगा. Is this making sense?
Yes, sir.
Okay, so if there is a mode in one direction and Py is also in that direction, then Py is adding to your moment.
Yes,
If
sir.
Py is in the opposite direction, Py is subtracting from your moment. Okay.
Yes, sir.
Now, similarly in the stiffness, in the sense, what is the stiffness? The stiffness is the जो भी तुम्हारे और जो भी तुम्हारे displacement है, वो दोनों का जो what do you call it linear we say like we are dealing with linear dimensions. So in the linear analysis, the proportionality factor between your forces and displacement is your stiffness.
Yes, sir.
Are we good with that?
Yes, sir.
Okay. So now when we look at somebody either speak something or turn off your audio, because otherwise we can get a lot of background noise. Now, the geometric stiffness, which is the stiffness caused because of buckling, it can either be additive to the flexural stiffness or detractive from the flexural stiffness. Are we good with this?
Yes, sir.
Now, if it is subtracted from the flexural stiffness and is equal to the flexural stiffness, what do you get as the effective stiffness? Right.
Yes, sir.
Now, if something has zero stiffness, what does it mean? That at the smallest force, you will have infinite displacement.
Yes, sir.
And that is buckling.
Yes, sir.
Okay. Now, I don't know whether this is the way you learn buckling, but this is another way of looking at it.
Okay, sir.
Okay, is this making sense to you? And इसमें एक physical sense आ रही है ना कि क्यों buckling हो रहा है.
Yes, sir.
Now this is exactly where my point is, that the buckling is creating eigenvalues and singularities, because every time a stiffness matrix becomes zero, that's a singularity.
Yes, sir.
Okay. Now it creates this singularity, and these singularities create unchecked responses that you do not get. You do not get finite responses. You end up getting infinite responses, and the infinite responses are because of the singularities created. Okay. So
Yes.
is trying to figure out how many singularities are actually being created in a structure, and finding out what is the lowest of the singularities ends up as becoming your Euler critical buckling load. You will get several singularities, but out of these several singularities, this is the lowest which is important, because यार अगर मैं 50 टन का लोड पहुंचना है तो 50 टन के लिए 40 टन तो पहुंचना पड़ेगा ना यार.
Yes, sir.
तो अगर तुम्हारी पहली सिंगुलरिटी 40 टन पे है और तुम्हारी दूसरी सिंगुलरिटी 600 टन है, तो 40 टन जो है वो तुम्हारे लिए कवर नहीं होती है, क्योंकि 40 टन के बियॉन्ड सोच ही क्यों रहे हो. दूसरे वाले तो पहुंचोगे ही नहीं, बिकॉज 40 भी स्ट्रक्चर टूट जाएगा.
Yes, sir.
You getting my point? So now, and this is exactly where the entire concept happens, that also there is a post buckling, because जैसे तुम्हारा force increase होता है वैसे तुम्हारा stiffness जो है वो भी completely change होता रहता है. It is not just that it in one particular direction. And I don't want to get into that, because post buckling ends up as becoming a non-linear analysis, and I have no desire to touch and deal with the mathematics of non-linear analysis at any point of time. But understanding that this in concept, what is so, which is why your Euler critical buckling, which is your lowest buckling, ends up as becoming the only important thing, because beyond that, we are saying that after that the structure has. Okay. Now, as you have a interaction between an axial force and a flexural displacement, which causes your buckling to happen, you will have an interaction between your flexural rotation, okay, and your torsional forces. And
Yes, sir.
why flexural rotation? Because energy है ना, force के साथ displacement जाता है, because force into displacement virtue के हिसाब से energy generate करेगा. Torque के लिए energy generate करने के लिए दूसरा एक rotation होता है ना? So the flexural rotations, the torsional forces will also cause what would be a geometric stiffness matrix. But that geometric stiffness matrix is not force dependent, it is torsion dependent. And that is generating what is called a flexural torsional buckling. Okay?
Yes, sir.
I mean, in principle, इसका फिर मैथ्स अलग है, और मैथ्स अगर तुम्हें एंथू है तो हम करेंगे, बाकी तुम्हें एंथू नहीं है तो हम नहीं करेंगे. Is this making sense, guys? Until now, is it making some kind of qualitative sense? I'm not even looking at it as quantitative sense. And these are the different kinds of stress.
Conceptually, it's
I
okay.
think there's a है ना, बस अभी तो conceptually तक ही रहने दो यार. इतना ओके है ना तो ये बहुत बड़ी चीज है. Okay. So, any questions? Because I think we are very close to the end of our class. Questions, anybody? I think वो नहीं होने चाहिए, because वो जैसे आ रहे हैं वैसे तो तुम पूछते ही जा रहे हो, तो फिर end of the day क्या ही questions होंगे. But कुछ है तो पूछ लो. Oh my God, I didn't start that. I'm so sorry, Priyanka. From next time I'll do that. I'm so sorry, I'll start the recording. And I didn't even see your message because I can't see it because PPT cover करती है मेरे screen. Anyway, any questions, guys? नहीं होंगे तो done. So
Yes, sir.
I'll meet you on Friday. Okay. Have a
Thank you,
great
sir.
day and enjoy yourself.